Now let's test a more specific query. Blue colored Puma shirt for kids. The application successfully retrieves products that are related to the keywords Puma, Blue, and Kids. The results include the relevant product information and associated attributes available in the graph. This basically demonstrates how we can build a simple graph RAG application using Neo4j and Ollama without relying on OpenAI APIs or any cloud-based models. In today's video, I will show how to build a simple graph RAG application using Neo4j and the Ollama model without using any OpenAI API keys or cloud-based AI services. Everything in this project runs locally using free Ollama models. The goal of this application is to create a search system for a fashion dataset. I already have a sample fashion related data stored in Neo4j graph database, and I want to use graph RAG to enable product search. The dataset contains information about clothing products and their attributes, such as brand, color, category, material, and product type. With this setup, users can search using natural language queries like show me all black t-shirts, find red hoodies, display blue jeans from Levi's, etc. The system will understand the query and return the most relevant products from the graph database. The first requirement for any graph RAG application is the data itself. For this project, I created a sample fashion dataset containing around 1000 products. The data is stored in Neo4j as nodes and relationships. Each product is represented as a node, and its attributes are connected through relationship. For example, a product node might have relationships such as has color, has type, belongs to brand, made of, etc. Every product in the database is connected to its attributes in a similar way. The quality of a graph RAG system depends heavily on how the data is modeled. If you are working with a different dataset, make sure to identify the key entities and the relationships between them before importing the data into Neo4j. Different datasets have different relations. For example, products can be connected to brands, categories, colors, and materials. Employees can be connected to departments and skills. Movies can be connected to actors, directors, and genres. If your data currently existing in a relational database, PDFs, Excel files, or documents, you will first need to convert into a graph structure. This typically involves identifying the main entities, extracting the relationship between those entities, creating nodes and relationship in the Neo4j. Once the data is properly modeled as a graph, it becomes much easier to build graph RAG applications that can understand relationships and provide more accurate search results. Before we start, I want to mention that this is a very basic graph RAG implementation. I am not using any advanced graph RAG techniques or complex retrieval strategies. The goal is to understand the core concepts and build a working application from scratch. So let's first understand the overall architecture. In the first step, when a user enters a search query such as show me black t-shirts, the application first extracts the important keywords from the query. Then, the extracted keywords are converted into vector embeddings. Similarly, the nodes and relationship stored in the Neo4j graph database are also converted into vector embeddings. In the third step, using vector similarity search, the application compares the query embeddings with the embeddings of nodes and relationships in the graph. This allows us to find semantically similar terms even when the exact words do not match. The matching nodes and relationships are then returned as relevant results. In the fourth step, based on the matched graph elements, the application dynamically creates a Cypher query. The query is executed against Neo4j to retrieve the actual data from the graph database. In the final step, the retrieved graph data is then sent to an LLM. The LLM analyzes the retrieved information and generates a natural language response for the user. So that is the complete flow of this architecture. Now let's look at the tools and softwares required for this project. Install Ollama. First, you need to install Ollama, which allows you to run large language models locally on your machine. Visit the Ollama website, install it, and make sure it is running correctly. Download the required models. In this application, I am using two different models. Nomic Embed Text for generating vector embeddings, DeepSeek R1 1.5b for generating the final response. You are not limited to these models. You can also try with alternatives such as Qwen, Mistral, Llama, etc. To download these models, run this command. Install Neo4j. Next, we need a graph database. For this project, I am using Neo4j Community Edition, which is free and sufficient for building GraphRag applications. After installing Neo4j, create a database and import the graph data. I have already created the nodes and relationships required for this project. I will also provide the dataset used in this tutorial so that you can easily import it in your machine. Now let's start building the application. The first step is to load all the entities from the graph database and convert them into vector embeddings. To do that, I am using load entities method to fetch all the entities from Neo4j. Once the entities are loaded, I use the build entity embeddings method to generate vector embeddings for each entity. This process creates embeddings for all the nodes and store them in memory, which will later be used for semantic search. Now that we have vector embeddings for all the graph entities, the next step is to process the user's query. Before we can compare the query with the graph embeddings, we need to extract the important keywords from the user's question. For example, if the user searches for "show me red hoodies from Levi's," we first split the query into individual words and then try to find semantically similar entities in the graph. For this, I created a method called semantic entity lookup. This method takes each keyword and searches for related entities within the graph embeddings. The main logic is implemented inside the find similar entities method. This method uses cosine similarity to compare vector embeddings and identify the most relevant matches. For generating all these embeddings, I am using the Nomic Embedded Text model from Ollama. Once the search is complete, the semantic entity lookup method returns a list of matched entities from the graph database, retrieving products from Neo4j. At this point, we have identified the relevant entities that match the user's query. Build product query. This function builds a dynamic Neo4j Cypher query for product retrieval. The next step is to retrieve all the products connected to these entities. To do that, I created a method called retrieve_products. This function is responsible for fetching the most relevant products from Neo4j based on the semantic search result. So basically, this function builds a Cypher query using the matched entities, executes the query against Neo4j, retrieves the matching product nodes, generating the final answer. Now we have everything we need from the graph database. The final step is to send this retrieved information to the LLM and generate a natural language response. For this, I created the ask_LLM function. This function sends two things to the model: the user's original question, the product information retrieved from Neo4j. I am using DeepSeek R1 1.5b running locally through Ollama for this step. The quality of the response depends heavily on the prompt. So I provide the clear instruction to the model, such as use only the retrieved graph data, do not invent products or attributes, return structured products summaries, etc. These instructions ensures that the model stays grounded in the graph data and produces accurate responses instead of hallucinating information. Now that all the code is ready, I have shared the code and you can find the link in the description below. I have added all the methods into a single file called semanticsearch.py. For testing, I have included a sample query in this file. When we run the script, the application first performs semantic search on graph entities and finds the most relevant matches. As you can see, the output displays the semantic similar entities found in the graph, their similarity scores, the matching product details retrieved from Neo4j. This helps us to verify that the semantic search is working correctly and that the system is able to identify the relevant products based on the user's query. So that's it for the code walkthrough. I have organized all these scripts and built a simple user interface using Streamlit, making it easy to interact with the GraphRag application. To set up the project, on your machine, clone the GitHub repository, create and activate a Python virtual environment, install all the required dependencies from the requirements file, configure Neo4j and make sure Ollama is running with the required models. Once everything is set up, start the application using this command. After running the command, the Streamlit application will launch in your browser. As you can see, the application is now up and running. Now let's ask some questions. Find blue hoodies with brand Nike. As you can see, the application retrieves products that match the color blue and the Nike brand. Along with the results, it provides a structured summary containing attributes such as brand, color, category, size, and other available product details. The products are fetched directly from the graph database and presented in an easy-to-read format. Now let's try another query. Women's t-shirt in size is. Here again, the system returns relevant products and displays the attributes in a structured manner. The model uses the graph data to identify products that best match the user's requirement. Now let's test a more specific query. Blue colored Puma shirt for kids. The application successfully retrieves products that are related to the keywords Puma, blue, and kids. The results include the relevant product information and associated attributes available in the graph. Keep in mind that the exact response format may vary depending on the prompt used for the language model. Overall, this application provides a reasonably accurate and structured results by combining semantic search, graph retrieval, and LLM-based response generation. It is important to note that this application does not guarantee 100% accurate results. The quality of the results depends on factors such as data available in the graph, the embedding model being used, and the retrieval strategy. However, it is capable of providing reasonably relevant and structured answers for this dataset. This basically demonstrates how we can build a simple GraphRag application using Neo4j and Ollama without relying on OpenAI APIs or any cloud-based models. Now let's discuss some of the trade-offs of this application and how we can improve it. The first challenge is semantic understanding. Since we are relying on the embeddings and graph retrieval, some user queries may not perfectly match the terminology stored in the graph. This can be improved by using stronger embedding models and combining vector search with graph search. The second challenge is graph expansion. As the graph grows, retrieving too many connected nodes can increase the response time and create very large prompt for LLM. A simple solution is to limit retrieval to the top relevant nodes and perform only a small graph expansion. Another limitation is context size. Sending too much graph data to the model can exceed the model's context window. To avoid this, we should retrieve only the most relevant products and summarize the graph context before sending to the LLM. Finally, as the product catalog grows, embedding storage and retrieval become important. Instead of storing embedding in Python memory, we can use Neo4j's vector indexes for better scalability and performance. So that's all about the GraphRag. I hope this tutorial helped you understand the fundamentals of GraphRag and how graph databases can be combined with local LLMs to create intelligent search applications. If you found this video helpful, don't forget to like and subscribe. Thank you for watching and see you in the next video.